Hi everybody, today we're going to continue our work with inequalities, but now we're going to be graphing linear inequalities. So a lot of the work we do here will kind of go back to our work with chapter 2 when we were graphing equations of lines. So we're kind of using the skills we used in chapter 2 as well as what we've learned so far with inequalities. Now, when we talk about solutions of linear inequalities, these inequalities are going to have lots and lots of correct solutions. So just to think back, we've been working with things that look like this. For example, and we know to solve that we subtracted 2. And so we got x is less than 1. So we can even think of when we were graphing it. We know that this looks something like this. So all of the points I'm shading in to the left are solutions of that inequality. Remember, when we talk about a solution, we mean that it makes the inequality true. So, for example, if my solution was x is less than 1, I know that negative 2 is part of that solution. So if I plug negative 2 into my original, I would have negative 2 plus 2 is less than 3. Well, this is just 0 is less than 3, which is a true statement. So negative 2 is an example of one of the solutions that make that inequality true, but we have lots and lots of those. Now, the difference here, before when we were working with inequalities, they only had an x. When we talk about linear inequalities, these are going to have an x and a y variable. Just like when we were graphing equations of lines, linear inequalities now have an x and a y variable, and just like our simple inequalities, they're going to have lots and lots of solutions. So the first thing we need to be able to do, this example says find a solution, but really what we're going to be asking you to do is to determine if a point, so let's maybe say in this case 0, 0. So determine if the point 0, 0 is a solution of the inequality y is less than 2x minus 3. So that's what it might look like. I know I have a linear inequality here because I have an x and a y, and I'm being asked if this point is a solution. So here's what we're going to do. I know this ordered pair, this represents x, and this represents y. So what I'm going to do is plug those values in for x and y. So my y is 0. I have a less than 2 times. My x is also 0. And then I have minus 3. So if I simplify this, I have 0 on the left side. 2 times 0 is 0, minus 3 is a negative 3. Now, I know that 0 is actually not less than. I draw a line to represent that. It's not less than negative 3. So I would say that 0, 0 is not a solution of that inequality. So there are lots and lots, but there are some points that are not solutions. So we'll just do a couple of these examples, maybe 1 and 2, so we can get an idea for what the directions will look like and what work we need to show. So my example says, my directions, tell whether the ordered pair is a solution of the inequality. So they're going to give you a linear inequality and an ordered pair. So we're going to do just what we did before. I know this is my x and this is my y. So in my inequality, I see x comes first, so I'm going to do 0. Then I copy minus 3. Now for y, I'm also going to plug in 0. And then I'm testing if that's less than or equal to 6. So I'm going to evaluate that. I have 0 minus, let's see, 3 times 0 is 0. So 0 minus 0 is just 0, is less than or equal to 6. Since this is true, I would say 0, 0 is a solution because it makes that inequality true. Let's try number 2. It's the same inequality, but a different ordered pair. Idea is still the same. Here's my x and my y coordinate. So for x, now I'm going to plug in a 6. I have minus 3. In for y, I plug in a negative 1. And then I'm checking if that's less than or equal to 6. That's my question. So let's see, this negative times a negative is a positive. So I have 6 plus 3 would give me 9 is less than or equal to 6. Obviously 9 is not less than or equal to 6. So I would say the ordered pair 6, negative 1 is not a solution. So that's the first piece of this, is just being able to test whether a point is a solution. The real big piece of this, however, is what we're going to get into next, and this is talking about how we graph linear inequalities. So we're going to go over to the next page. I'm going to give you some kind of basic steps here, and then we'll do some examples. Now, just like we graphed in Chapter 2, we always worked with slope-intercept form. And hopefully we all remember slope-intercept form was y equals mx plus b, where m is the slope and our b is the y-intercept. So we're going to be using this same idea to graph. The only difference is instead of having an equal sign now, we're going to have some kind of inequality symbol. So our first job, just like when we were graphing in slope-intercept form, our first job is always going to be to isolate y. By that I mean get y by itself if needed. So sometimes y is already going to be by itself, and sometimes we'll have to do the work to get it by itself. So we're going to isolate y, and then we're going to graph the line using slope-intercept form. Now, there's going to be a little something different here. So when I say graph the line, really I guess I'm saying plot the y-intercept and a second point using the slope. So actually we're just going to plot those 2 points in the second step. In the third step, we're either going to connect the points using a solid line or a dashed line. And we'll get into that a little more later, but solid is really going to happen if our inequality is either greater than or equal to or less than or equal to. And dashed is going to be if I'm strictly greater than or strictly less than. And by dashed, I mean it's going to have gaps in it, like that, as opposed to a solid line like this. All right, and then the last thing, we're going to have to shade the solution set, I'll say. And again, we'll get into that more. But basically, we're either shading above the line or below. And the symbols associated with that, if I'm shading above, that means I had a greater than or equal to. If I'm below, that means I had a less than or equal to. Now, I know right now this is just a list of steps. It doesn't mean a whole lot. So let's go through some examples so you get an idea of how this works. So here's our example. Just really quickly, I'm going to kind of recap what we said in steps 3 and 4. So my line is going to be solid if I had one of these two symbols. It's going to be dotted, just like it is in this box, if I have just a greater than or just an equal to. This is kind of similar to in our old inequalities where we had the closed circle and the open circle. Now, shading above is going to be anywhere I had a greater than or equal to. Shading below is a less than or less than or equal to. So now let's take a problem and kind of go step by step. So here's my linear inequality. I know it's linear because I have an x and a y, and I know it's an inequality because I have a less than symbol and not an equal sign. So my first step said to isolate y if needed. So obviously here y is not by itself, so that's the first set of steps we need to do. So this goes back to kind of chapter 2 again, thinking about how I get y by itself. So the first thing I need to do is move this 2x over. So when I do that, these cancel. I'm left with a negative 3y. I subtracted, so my inequality symbol does not change. Now I'm going to grab my negative 2x, and since this is a positive 12, I'm going to have plus 12. I don't combine those because this has an x and the 12 does not, so they can't go together. Now the last thing I need to do is divide by negative 3 everywhere. When I do that, since I divided by a negative, I know my inequality is going to flip. So I'm going to make a note there. So now I have y is greater than. Here, if I put this in my calculator, the only simplification I can do is make it 2/3, a positive x, and then 12 divided by a negative 3 gives me a negative 4. So my equation, my inequality, excuse me, it's not an equation. My inequality is y is greater than 2/3 x minus 4. So we just did step 1. We got y by itself. So now we're going to plot some points here. We're going to plot our y-intercept. Now in this case, right, whenever we're graphing, we know we have an m and a b. In this case, my m is 2/3 and my b is a negative 4. So when we're graphing in slope-intercept form, we start by plotting our y-intercept, which is negative 4 here on the y-axis, and then we use our slope, right, to locate a second point. So in my case, my slope is 2/3. So that means I'm going to do rise over run. I'm going to rise 2 and run to the right 3. So up 2 over 3. All right, so that's step 2. I've got my 2 points. Now, step 3 told me connect the points using either a solid line or a dashed line or a dotted line. In our case, since our symbol is strictly less than, that means I'm going to use a dotted line. So when I connect my 2 points with my straight edge here, I'm not going to draw a solid line, but I'm going to leave spaces. So I'm making a dotted line. And I still put my arrows on either side. All right, now I know that either the points below this are going to be solutions or the points above are going to be solutions. So now I have to decide, since I have a less than symbol, that means I'm going to shade below. Oh, I'm sorry. I need to look down here. I'm looking at this symbol and I'm a greater than symbol. That tells me that I'm going to shade above the line. I have to look at the form where y was isolated. So I'm going to shade above. So what I usually do is I just kind of show that like this. That means everything in this purple area, all these points are solutions of that inequality. They make it true. And we could test that. That means that if I'm correct, this point 1, 2, let's say, anything in this area should be a solution. So let's check if 1, 2 is a solution. My original inequality was 2x minus 3y is less than 12. So if I plug in my x and my y, I should get a true statement. So I have 2 times my x was 1 minus 3 times my y value, which was 2. That should be less than 12 if I've done this right. So I have 2 minus 6, which is negative 4, which is indeed, sorry about that, less than 12. So I know I've done it correct. I know I've shaded in the right spot. So that's what we mean about all these points being solutions. I could plug any of these into my original inequality and get a true statement. Now I know this has been a long video. I'm going to do one more example and then we can do some more in class tomorrow. Let's go ahead and do, now the nice thing here is that if you look at all these examples, y is already isolated. So we don't have to do that work. So let's look at number 4. And then we'll do some more in class to start tomorrow. So in number 4, my y is already isolated. I'm done with step 1. Step 2, I know I need my m and my b so I can start plotting points. My m in this case is the 1, so my slope is 1 over 1. My b is a positive 4. So I'm going to go ahead and plot my b value at positive 4. And I'm going to plot another one by rising 1 and running to the right 1. So up 1 over 1. Now in this case, I have a less than or equal to. So that means I'm going to do a solid line. So just like we used to graph, I'm going to connect these with a solid line using my straight edge. And now the only thing I have left to decide is where to shade. Since it's a less than symbol, I'm going to shade below the line. So that means anything underneath. If you think about walking on the line here, I want to shade below where I'd be walking. And this is how I represent that. So again, the idea is any point in this purple region should be a solution. And I see actually 0, 0 here is an easy one to test. So my original inequality was y is less than or equal to x plus 4. So here I have my x and my y. Let's substitute and see if we've got this right. So y would be 0. It says that's less than or equal to, my x is also 0, and then plus 4. If I simplify, I get 0 is less than or equal to 4, which is a true statement, so it tells me I shaded on the correct side. Alright, I know that was a lot for this video, so I appreciate you hanging in there and taking good notes. We'll do a couple of practice problems before we start class all together, or at the beginning of class I should say. We'll do some practice problems together before you start individual practice. Alright, see you tomorrow.